Alright, welcome everyone. So in this video we're going to talk about stoichiometry. We're going to talk about all these concepts in stoichiometry: the molar mass, the moles, chemical equations, reagents, of course solution stoichiometry, and we're going to solve these exam questions at the far end to just familiarize ourselves with stoichiometry. So basically, what are the basics? What is stoichiometry itself? So stoichiometry is the calculation part of chemistry. The calculation part. So what we mean here is that it's going to answer common questions like how much reactants do I need? It's also going to answer questions like how much product will I get? Then for the most part, stoichiometry is also going to answer which reactant will finish first, which we usually call the limiting reactant, and we're going to talk about this as we proceed. So if you ignore stoichiometry, you are basically ignoring the heart of chemistry. So by the end of this video, you should be able to explain what stoichiometry means, understand the mole concept, also use the Avogadro's number, which we're going to talk about, and you should be able to calculate the number of moles, the number of particles, and most importantly, avoid the most common mistakes people make. Okay, so basically, what is the mole concept? The mole concept, this one is the core of stoichiometry, because a mole, in simpler terms, this is just a counting unit. Now this is very important, because the way you can code 12 eggs to be equals to 1 dozen or a dozen, that's the way you're calling a mole as a counting unit. If we say 100 years, we know that 100 years is equivalent to 1 century. Okay? If we say 20 years, 20 years, that gives us a score. If we say 10 years, 10 years, that's a decade. Okay, so basically some of these concepts are very fundamental if we want to understand what a mole is, because in chemistry 1 mole of a substance is equivalent to 6.02 times 10 to the power 23 particles. Now we have to understand that these particles that we're talking about, they can be, number one, they can be atoms. These particles can be molecules, and these particles can be ions. And this number that we've just written here, this one, we call it the Avogadro's number. The Avogadro's number. Okay, so that is very important for us to understand. Now someone would ask, why a number so big? Okay, why is a number so big? And that's a very good question, because if you're going to look at this number 6.02 times 10 to the power 23, this number equates to like 6022, and you have to put like about 19 zeros. That's a very big number. But why this big number? Okay, what you should realize is that atoms themselves, if you're going to talk about atoms are extremely small. Okay, so to get a measurable amount, we need a huge number of them. So if we say 1 mole of carbon, 1 mole of carbon atoms. What this should give us is the same, the Avogadro's number, 602 times 10 to the power 23 carbon atoms. Okay, so the same thing, if we say want 1 mole of water molecules, it should give us 6.02 times 10 to the power 23 water molecules, and that is very important. Now in exams they love asking how many particles are in a given number of moles. So we have to know formulas that link moles and particles, and it's very important. So the formula that we use, the number of particles, and we've just talked about what these particles can be. These particles can be atoms, they can be ions, or they can be molecules. Okay, so the formula is the number of particles will be equals to the number of moles multiplied by the Avogadro's number times 10 to the power 23. Okay, so basically that. Now how do we apply this? Let's solve a question. In this question, how many atoms are present in 2 moles of sodium? So basically we have moles, now we are converting to the particles. In this case, how many atoms specifically, to be specific actually. So in this case, if we're going to look at this question, we have to identify what we've been given. The number of moles that we've been given, it is 2. Okay, then we already know the Avogadro's number. So in this case, what would be the number of atoms? So we said the way we find the number of atoms or particles, in this case is going to be what you have as the moles. We have 2 moles, so we're going to have 2 moles. We're going to have 2 moles multiplied by what do we have as particles? In this case, we've got 6.02 times 10 to the power 23. Then basically you just have to multiply these two. Okay, so 2 multiplied by 6.02 times 10 to the power 23, I'm getting about 1.204 times 10 to the power 24 atoms. Okay, so basically this will be moles per, or atoms per moles. Okay, so the more and the more are going to cancel, and you're just going to have atoms there. So that is very, very important for us to understand. Now this is where many students make mistakes, because number one, they tend to forget the power of 10. Okay, and then for the most part writing the wrong unit. If they've asked you atoms, please write atoms. If they've asked you molecules, write molecules. So that is very, very important. Always end with atoms, molecules, or ions. Let's you can also try another one. In this case, let's say if they ask you how many molecules are present in 0.5 moles of carbon dioxide. So the way we're going to solve this is the same thing. Since this time around they're asking us, let's say, how many molecules. So you're going to get your 0.5, you multiply it with your Avogadro's number, and you get your answer. So basically that. Now, what are some of the things that we've just talked about as an introductory part? We've talked about stoichiometry. Stoichiometry is the calculation part, okay, of chemistry. Then we've talked about a mole. A mole is a counting unit. Then we've talked about the Avogadro's number, which I'm just going to write as Na, which is equivalent to about 6.02 times 10 to the power 23 particles. the Avogadro's is going to help us convert between moles and particles. Okay, very important. Now let's talk about molar mass and mass or mass to mole calculations. Now this is where stoichiometry starts to make sense, because in exams just this part alone can earn you about 20 to 30% of your chemistry mark. So by the end of this part, you should be able to explain what molar mass is. You should be able to calculate molar mass specifically from the periodic table, and for the most part converting mass to moles or vice versa. Okay, that is very important. So in this session, if we're talking about molar mass, okay, if we're going to talk about molar mass, you should understand one thing, that most stoichiometric questions in exams, they always start like calculate the mass of, okay, most of them. Other exam questions, they'll be like how many moles, maybe are present in grams of this and that. Now able to see we're talking about the mass and the moles. Now someone would ask why this topic is very important. The reason is very simple. If you're going to look at in real life, chemists mostly they measure mass, okay? They barely measure moles, but mass they do measure. However, if you're going to go in industries, mostly industries, you're going to be weighing chemicals. Now, as you weigh those chemicals, you want them after that you convert to moles. That's where this topic is very important, because it helps you, combine what you have in the industry and, just as a chemistry like that. So molar mass is the bridge between theory and reality in simple terms. Then what is molar mass? So we have to understand what molar mass is. The mass of 1 mole of a substance is what we call molar mass. Okay, so the units it's going to be grams per mole. Okay, so this is grams per mole, and that is very important for us to understand. Now, just to remind us, we've said every time you're talking about mass is measured in grams, okay? Then the amount itself, okay, of that mass is the one that you measure in moles, okay? The link between the two, okay, the link between the two is what we are calling molar mass. Molar from moles, mass from grams. So that is very important for us to understand. Now, where you're going to get your molar mass from, you can get it from the periodic table. For example, if I get sodium as an element, sodium is Na. Now, sodium on the periodic table, from the periodic table, its atomic mass is about 23. That's its mass. So therefore, what will be its molar mass? So the molar mass will just be 23 grams per mole. Okay, so that is easy. What if we're talking about water? For water, what would be its molar mass? So hydrogen has a mass of 1, oxygen has a mass of 16. Now look at our calculations here. We've got 2 hydrogens, okay? So in this case, I'm going to multiply the first one by 2. Therefore, what am I going to have? I'm going to have 2 for hydrogen. I'm going to have 16 for oxygen. Now when I add 2 plus 16, I'm just going to get 18. So that will be our molar mass. Now molar mass has units, so this is going to be 18 grams per mole. Easy, right? Let's solve another one. Now here we really have to pause, okay? Because students sometimes they tend to forget multiply, or to even multiply by subscripts. They ignore brackets. Very important. So for example, if I've got calcium oxide, calcium hydroxide, then I've got a 2 down there. How do I solve this one? So I'm going to get my calcium, oxygen and hydrogen. Let's start with calcium. Calcium, it has roughly its molar mass is about 40, okay? Oxygen is 16, hydrogen it's 1. Now you always have to consider the subscript, which is 2. In this case, the oxygen, which has in this case the molar mass of 16, I'm going to multiply by 2. Same with the hydrogen, because of the subscript that we have. Then we solve. So we're going to have 40. 16 multiplied by 2, that is a 32. 2 multiplied by 1, that is a 2. Then I'm supposed to add 2 plus 2, that is a 4. Then 7, that is 7, yeah. So we're going to have 74. But now you have to express it in the in terms of molar mass. That would be grams per mole. So basically that, very important for us to understand. Someone asked, what is the most important formula in stoichiometry? Of course, there are many of them, okay? But this one is major, the one that combines everything, okay? The number of moles it is equals to the mass over the molar mass. Okay, so that is very important. We've talked about the number of moles. Mostly industry people, they want moles. The mass, mostly chemists want that mass. Then the molar mass is you relating the moles and the mass, and it's very important for us to know this this equation. Now let's solve some questions. Let's say you want to convert mass to moles, okay, based on that formula, because it's a relationship that just incorporates everything. Now, how many moles are present in 36 grams of water? So we're going to write our formula. Number of moles is equals to mass over molar mass. We're finding the number of moles. In this case, the mass, we've been given that it is 36 grams divided by the molar mass. The molar mass of water, we've been calculating it, it's 18 grams per mole. Now notice something. We've got 36 grams divided by 18 grams per mole. Now every time you're dividing, you're going to have multiplication. So in this case, I'm going to have multiplication. The mole is going to go on top, then down I'm going to have 18 grams. Okay. Now the gram and the gram can cancel. I'm just going to have 36 more on top divided by 18. Now 36 divided by 18, that is just a 2. Okay. So this one is going to give us 2 moles. Okay. That's how you convert mass to moles. We've converted 36 grams of water to 2 moles. Okay. So basically that's very important for us to understand that part. What about the vice versa? Let's say you want to convert moles to mass. And we have a question here, what is the mass of 0.5 moles of sodium chloride. Okay, so let's first find the molar mass, because for us to be able to find the mass, it's like we're going back. Number of moles is equals to mass over molar mass. Now if I make mass the subject of the formula, I'm going to have mass will be equals to number of moles multiplied by the molar mass. So I'm supposed to find the number of moles. Actually, we've been given the number of moles is 0.5, but I'm also supposed to now find the molar mass for sodium chloride. So in this case, the molar mass, since we've got two elements, sodium and chlorine. In this case, what is sodium? On the periodic table, sodium has a molar mass of 23. Chlorine has a molar mass of about 35.5. Okay, I'm supposed to add these two. So 23 plus 35.5, I'm getting 58.5 grams per mole. Okay, so basically that we found that. So now what do we now do? We just need to replace the number of moles we've been given, that is 0.5 mole. This is multiplying by 58.5 grams per mole. Okay, now what is now going to happen is that we can cancel the mole and cancel the mole. Okay, therefore we are going to have 0.5 multiplied by 58.5. So on my end, I'm getting 29.25 grams. Okay, so basically this is how we solve, these type of questions. Then you can just practice, just a pause here. You can pause and try this question. If you are able to answer this question confidently, then we are getting there. And it's very, very important for us to also review this part. Now, we've talked about some of the basic concepts. Please, as you are moving on, you can also subscribe to our channel. Hit on that like button to just, help us with the work that we do. Now, let's keep the momentum. Chemical equations, balancing mole-to-mole calculations. Now, up to now, we've learned what the mole is, how to convert between mass and moles. Now comes the game changer, chemical equations. Because, stoichiometry does not work without a balanced equation. In exams, if your equation is wrong, the whole calculation is wrong, even if your math is perfect. So this part of stoichiometry is non-negotiable. So by the end of this part, you should be able to know how to write chemical equations, how you balance them, and how you use coefficients to find more ratios. Now someone would ask what a chemical equation is. So this is just an example of a chemical equation. A chemical equation shows reactants on the left, then it also shows products on the right. So basically that. Now, what are we supposed to understand? If we're going to write this one in terms of as a chemical equation, this equation is going to be hydrogen, in this case is going to be H2, plus oxygen, it will be O2. This is giving us water. Water is H2O. Now we have to balance this equation. Now the way we balance equations, you just have to count atoms on both sides. So if, let's say, this is our left hand side, this is our right hand side. So the question is, how many hydrogens are there, how many oxygens are there? Also on the right hand side, how many hydrogens are there and how many oxygens are there? So let's start with the hydrogens. How many hydrogens are there? Currently we have 2. How many oxygens? We also have 2. Okay, but when it comes to the right hand side, how many hydrogens are there? We've got 2. And how many oxygens? We only have 1 there. So because we've got 1 here, we are going to put a 2 in front here. Now because we've put a 2 in front, now how many hydrogens do we have? We have 4 hydrogens. Okay, now when we come on the other side, we only have 2 hydrogens, so it means I'm supposed to also put a 2 there. When I put a 2, now I also have 4 on my left hand side. Then is oxygen balanced? Here we have 2, even here we have 2. So basically that is how we balance equations, and that is very, very important. Now that we've talked about this, we also have to understand what we call mole ratios. This is the heart of stoichiometry. Now listen carefully. The coefficients in a balanced equation, they represent mole ratios. Okay, so these are the coefficients. We call them stoichiometric coefficients. These ones, the ones that are in a balanced chemical equation, they are going to help us so much. Okay, so that is very important. So now like in our previous equation, we had hydrogen plus oxygen giving us water, like that. Now what this means is that in terms of mole ratios, you've got 2 moles of hydrogen, react with 1 mole of oxygen to produce 2 moles of water. Okay, so this ratio is what we use in calculations. So basically that is very important for us to understand. So to just even assimilate it better, let's solve the equation. Let's say you want to convert moles to moles. Okay, the moles of one substance to the moles of another one. So we have a question there. How many moles of water are produced when 3 moles of oxygen react completely with hydrogen? Okay, so first you have to write the balanced equation. In this case, hydrogen plus oxygen giving us water. Okay, to balance it, I'm going to put a 2 there, I'm going to put a 2 there. Now that the equation is balanced, we have to find the mole ratios. Okay, now you're able to see that the ratio of oxygen and hydrogen, oxygen as a coefficient of 1, hydrogen as a coefficient of 2. So this is the ratio between the two. Now what this ratio means is that 1 mole of oxygen is going to give us 2 moles of hydrogen. Now this question is asking us when 3 moles of oxygen react completely with hydrogen. So if let's say now we are putting 3 moles of oxygen, how many moles are we going to produce for hydrogen? That's what this question is trying to achieve, more calculation. Okay, so in this case I'm just going to cross multiply. Okay, I'm just going to have x will just be equals to 2 multiplied by 3 moles. Okay, in this case I'm just going to have 6 moles. So how many moles of water are produced? 6 moles of water are going to be produced. Why I'm saying 6 moles of water is going to be produced, because whatever I'm going to have as the moles of hydrogen, that will be the same as the moles of water, because they have the same coefficient. They have the same stoichiometric coefficient, and that is very, very important for us to understand. So we're able to see that balanced chemical equations are essential. Coefficients give you the mole ratios. More to more calculations, they use ratios, not mass, and that is very, very important for us to understand. So this is another question that you can try. Just to pause the video to just try. So if you can solve this confidently, then you are mastering stoichiometry. Then a quick reminder, don't forget to like, to subscribe to this channel. Okay, then let's do a quick recap. We've talked about the moles, the mole concept, just as the basics. We're just from talking about balancing chemical equations. That is very important. Then also some coefficients. Now let's talk about the limiting reagent and the percentage yield. Now we move to the topic that scares most students, but I promise you something. Once you understand this part, you actually like it. Why? Because this is one of the highest tested stoichiometric topics. It's going to appear in your tests, in your quizzes, in your practical exams, even in your final examination. And the good news is that, the questions, they follow a clear pattern. So by the end of this part, you should be able to define what a limiting reagent is correctly, how to identify the limiting reagent in reactions, and also how to calculate the amount of product that is going to be formed. Of course, also understanding what we call the excess reactant. Then you should be able also to understand the other part, what we call percentage yield. Okay, so now what is a limiting reactant? So let's start with a simple idea. Let's say imagine you're making sandwiches. Now we've got, let's say, 10 slices of bread. Then let's say you've got 3 slices of cheese. So now if we say each sandwich, let's say it needs 2 slices of bread, and let's say 1 slice of cheese. Now the question would be, how many sandwiches can you make? Now you're able to see that even though bread is plenty, cheese runs out first. Okay, so you're going to realize that cheese in this case will be the limiting reagent. Now in simpler terms, the limiting reagent is just that reactant that is completely used up first. Okay, and it's called a limiting reagent is because it limits the amount of products that are going to be formed. Now that one that remains in excess, the reactant that remains is called the excess reactant, and it's very, very important for us to understand. Now how do we identify the limiting reactant or reagent? So for us to do that, you have to first write the balanced chemical equation. This is major. Okay, balanced chemical equation. Then when your equation is balanced, you have to now convert what you have, the quantities. Okay, what you are given quantities, you convert them to moles. Then after that, you are supposed to compare the mole ratios. Then you are then supposed to identify which reactant now produces less products, okay, or product. Basically that. By you doing this, you would have managed to identify the limiting reactant. Let's solve the equation. 2 moles of hydrogen react with 1 mole of oxygen, which is the limiting reactant. Okay, so this question is not complete. Okay, so this question is not complete. Okay, so let's put another question. Let's say I've got 5 we need grams. That's why I'm saying it's not complete. Let's say we have 5 grams of hydrogen, and this one reacts. Let's say it reacts with 20 grams of oxygen. Okay, then we are told to find the limiting reagent. So how can we solve this one? So first and foremost, you have to write the balanced chemical equation. So in this case, we've got hydrogen to react with oxygen, okay, to give us water. So you know how to balance this one. I'm going to put a 2 there, I'm going to put a 2. It's balanced. Now we're going to convert our masses to moles. We've got 5 grams hydrogen, 20 grams oxygen. Now let's start with us converting the moles of finding the moles of hydrogen. Hydrogen is going to be mass over molar mass. In this case, the mass of hydrogen, we've been given that it is 5 grams, okay, divided by the molar mass. The molar mass of hydrogen, since there are 2, what is it going to be? I'm going to have 2 grams per mole. Okay, now what is going to happen is that the gram and the gram are going to cancel. I'm just going to have 5 divided by 2, that is 2.5 moles of hydrogen. So we found the moles of hydrogen. Then let's find the moles of oxygen. So oxygen, its molar, its number of moles, it will be mass over molar mass as well. Now the mass, we've been given that it is 20 in the equation, so we have 20 grams divided by the molar mass of oxygen is 16. Okay, now that's 16 because there are 2 oxygens. We're going to have 32 grams per mole. Now according to your dimension analysis, the grams and grams are going to cancel. Therefore I have 20 divided by 32. 20 divided by 32, it gives me 0.625 moles. Okay, basically this. Now we have to check the products that have been formed. If we're going to do that, we have to also look at the mole ratios. So looking at the mole ratios, 2 moles of hydrogen reacts with 1 mole of oxygen. Okay, now the actual ratios, we've got 2.5 moles for hydrogen, 0.625 moles of oxygen. Now from just the hydrogen part, 2 moles of hydrogen, it gives us 2 moles of the product, which is water. Okay, and that is like 2.5. 2.5 moles is going to give us 2.5 moles of water as well, because they have the same coefficient. Okay, now if you're going to go for oxygen it's a bit different. So we have 1 mole of oxygen, it giving us 1 mole of oxygen giving us 2 moles of water. Okay, now if we're going to just solve this one, what are we going to have? Let me just rub for hydrogen. Hydrogen is maintained, there is nothing much, it's 2.5. We just want to find for oxygen. So oxygen, we said 1 mole of oxygen, this one is equivalent to 2 moles of the product. The product is water. Now oxygen, 1 mole of oxygen in the reaction gave us 0.625 moles. What about the other part? I'm just going to put x. Therefore we're going to cross multiply. This x will be equals to 2 multiplied by 0.625 is giving me 1.25. These will be moles of water that is going to be produced because of oxygen having a coefficient of 1. So basically, if you're going to compare 2.5 and 1.5, you're going to realize that oxygen, the one that gives us less, because it produces less water, oxygen is the limiting reagent, and that is very, very important for us to understand. Then on this topic, you're also supposed to understand what we call percentage yield. Now, in theory, reactions give a certain amount of product. What you get in theory, we call it the theoretical yield. Okay. So, however, if you're going to come in real life, some products is going to be lost, reactions sometimes may even not go to completion. So the actual amount obtained is called the actual yield. Now, the formula that is going to help us find the percentage yield, the percentage yield in this case, it will be the actual yield divided by the theoretical yield multiplied by 100%. Now, for us to assimilate it better, let's solve a question. Let's say a reaction produces 8 grams of product, but the theoretical yield is 10 grams. Calculate the percentage yield. Okay, so in this case, your percentage yield will just be equals to your actual over your theoretical multiplied by 100. In this case, the actual yield, we said this reaction produced 8 grams. Okay, so the actual yield is 8 grams. Then the theoretical yield, they've given us that is 10 grams. Then we're just going to multiply by 100. Now, what is now going to happen is that the grams and the grams are going to cancel. Then we've got 10. 10 into 10 is 1. 10 into 100, that is 10. So we have 8 multiplied by 10, which is 80. Since this is a percentage, it's going to be 80%. What this means is that this reaction, it gave us 80% of the product, although it just didn't give us an ideal, an ideal number, which is 100. So basically that, let's solve another question. Let's say this time around you combine limiting and percentage yield. Okay, what is going to happen? Let's say we have 10 grams of calcium carbonate and it decomposes to form calcium oxide and carbon dioxide. If 4 grams of calcium oxide is obtained, calculate the percentage yield. So you have to come up with a balanced chemical equation. So that will be calcium carbonate. This one, it has decomposed. So it's going to give us calcium oxide plus carbon dioxide. Now, what did we say? You have to convert, you have to find the number of moles of, this carbon or calcium carbonate. So in this case, the number of moles will just be equals to mass over molar mass. In this case, the mass, we've been told that it is 10 grams of calcium carbonate. Okay, so I'm going to put 10 divided by its molar mass. Calcium carbonate has a molar mass of about 100 grams per mole. Why? Because calcium is like 40, carbon is like 12, oxygen is 16. 16 multiplied by 3, that will give us 48. Okay, then if we're going to add now 52 plus 48, that will give us 100. Okay, roughly like that. So that is the molar mass for calcium carbonate. Now if we divide 10 by 100, that will give us 0.1. This is the number of moles, so it will be moles. Okay, so these are the moles for calcium carbonate. So allow me to just write it here, 0.1 moles. Okay, now when we come to the other part, if you are going to look at the mole ratios, this has a mole ratio of 1. Okay, the ratios are just 1 throughout. Okay, then the equation is rather balanced. So now what you should understand is that since they are in the ratio of 1:1, 1 mole of calcium carbonate is producing 1 mole of calcium oxide. Okay, so it means they're going to have the same number of moles, which is 0.1 moles. Therefore now we have to convert now to mass, because mass is the one that is going to help us find the percentage yield. So in this case, the mass will be equals to number of moles multiplied by molar mass. In this case, the number of moles is 0.1 moles multiplied by the molar mass for calcium oxide is what? Okay, so calcium is 40, oxygen is like 16, this is like 56. So we have 56. So I'm going to put 56 here, grams per yeah, 56 like that. Now what is now going to happen is that the more and the more are going to cancel. Therefore I'm just multiplying 0.1 multiplied by 56. Okay, what am I getting? I'm getting 5.6 grams. Okay, so that is what I have as the grams of calcium oxide, which is the product. Now what I'm now going to do is that since I found what we're supposed to obtain, I can now find the percentage yield. We've said the percentage yield in this case will be the actual that we were given. If say we've been given that 4 grams of calcium oxide is obtained, so here I'm going to put 4 grams divided by the theoretical, the one that we've calculated for calcium oxide, it is 5.6. So this is 5.6 grams. This will be times 100. Then I solve this, I'm getting 71.4%. So that is what is going to be our percentage yield. And this is about the limiting and the percentage yield. Now what we should understand is that the limiting reagent controls product's amount, okay, or the product that you're going to have in terms of the amount. Then you are always comparing moles, not masses. Please, moles, not masses. Then percentage yield compares actual versus theoretical. So basically that is a nutshell of what we've just talked about in this segment. Then okay, we've solved this one. Then we also have to understand another part of chemistry, which we call solution stoichiometry. Okay, now in solution stoichiometry we have to understand what we call concentrations and solutions. Okay, first let's define what a concentration is. Now the amount of solute that is going to be dissolved in a given volume of solution is what we call a concentration. Now the most common unit that is you are going to use for concentration in chemistry is moles per liter. Okay, so the formula for concentration that I don't want you to forget is that concentration itself is going to be the moles that you have multiplied by the volume. Okay, where your concentration is measured in mole per liter, okay, in mole per liter, but the number of moles here is measured as an amount of substance, then which is the mole. Then the volume is the volume here is measured in liters. So okay, so this should be division, moles divided by the volume. Okay, so that is how we find the concentration. So now you have to be able to convert between volumes and you know, you have to be able to convert volume to moles. Okay, so you can just manipulate the equation, since we are saying that the concentration is just equals to the number of moles divided by the volume. Okay, the volume in this case is in liters. So if you are trying to find let's say the volume here is just going to be the number of moles divided by the concentration. Okay, so basically this, please never forget this. It literally appears everywhere in solution stoichiometry. Let's solve some questions to just familiarize ourselves. So we're asked how many moles are present in 250 cubic centimeters of a 2 mole per liter sodium chloride solution. So we're trying to find how many moles, okay, that are present in that 250 centimeters. So now we have to convert our volume to liters, okay, and that is very important. We've got 250 cubic centimeters. Now we have to convert these to liters. So in this case, we're just going to divide by 1,000. Okay, so in this case, what are we going to have? We're going to have 0.25 liters. Okay, then we use the formula. The formula, we are saying how you find the number of moles. So the number of moles in this case is going to be the concentration over, actually, because it's the number of moles you're multiplying, because concentration is equals to, we've said concentration is equals to concentration, we've said it is equals to, if you're going to look at the equation that we had, we've said for concentration you are dividing, okay, what you have as the number of moles over the volume. But now, since in this case we're trying to find the number of moles, I'm going to make n the subject to the formula. So n will be equals to C multiplied by V. Okay, and that is what I wanted to talk about. Now in this case, what is the concentration that we've been given? We've been given that it is what? Okay, of 2 moles per liter. So we've been given, you see, 2 moles per liter of sodium chloride. So that is 2 moles per liter. We are multiplying this by the volume. Volume, we found that it is 0.25 liters. Okay, so now that we've got this, the liter and the liter are going to cancel. In this case, I'm just multiplying 2 multiplied by 0.25. So what do I get? So I'm getting 0.5. Now, since we're calculating the number of moles, we are going to have 0.5 moles. Okay, so basically this is how you solve this type of question. Okay, now let's solve another one. Let's say this time around we've got 225 cubic centimeters of 1 mole per liter hydrochloric acid reacts completely with sodium hydroxide. Then we're told to find the moles of sodium chloride used. Okay, so you have to come up with the equation. So we've got hydrochloric acid reacting with sodium hydroxide. Okay, so an acid and a base. So let's say this is hydrochloric acid plus sodium hydroxide. You know, every time you react a base, you're going to, a base and an acid, you're going to have a salt, which is sodium chloride in this case, plus water. Okay, that's a neutralization reaction. Now we have to find the moles of hydrochloric acid. Okay, so how are we going to do that? Because for us to find the moles of sodium chloride or hydroxide, we have been given little information about sodium hydroxide. We've just been told that it just the acid completely reacted with it. So it means we have to start from the hydrochloric acid going to the sodium chloride. Okay, that's why I find the moles of hydrochloric acid, because we literally have everything. So the moles of HCl, in this case, what am I going to have? We are saying if you are going to find the moles, okay, of HCl, in this case, if we're talking about the moles, we're saying you're multiplying the concentration multiplied by the volume. In this case, the concentration, we've been given that it is 1 mole per liter. Okay, so I'm going to have 1 mole per liter multiplied by the volume. The volume, we've been given that it is 25 cubic centimeters. Now, what are you going to do to that 25 centimeter? You have to convert it to liters. So it will be 25 divided by 1,000. This will give us 0.025 liters. So that is what I'm going to put as the concentration there, as the volume actually. So this will be 0.025 liters. So the and the liter are going to cancel. 1 multiplied by 0.025, I'm just going to have 0.025 moles of hydrochloric acid. Now, this is where mole ratios now come in to play a part. If you're going to look at the equation, is it balanced? Of course it's balanced. So if we look at hydrochloric acid we are saying it's 0.025 moles. Okay, now because all the coefficients are 1 in this case, whatever I have as the moles of hydrochloric acid, that will also be the moles of the sodium hydroxide, and also the sodium chloride. Okay, so basically that, and it's very important for us to understand that. So in this case, what will be the moles of sodium hydroxide? So sodium hydroxide will just have 0.025 moles as well. Okay, so basically that is how we solve this part. Now, I think for the most hour we've talked about stoichiometry. Let's talk about the rather last part of stoichiometry, which we call combustion analysis. Of course, the terms come to mind: empirical formula and molecular formula. Okay, so what do we understand here? So if you're talking about combustion analysis, this topic tests your understanding deeply, mostly on it involves you burning things in oxygen, formation of carbon dioxide and water. So a general combustion equation, it will be a hydrocarbon plus oxygen. This is going to give us carbon dioxide plus water. Okay, so when you burn a hydrocarbon in the presence of oxygen, you're going to have carbon dioxide and water. Now, for us to understand just this topic nicely, let's just solve some questions. So we've been given a question here. A hydrogen contains only carbon and hydrogen. When 2 grams of the hydrocarbon is burned, 6.6 grams of carbon dioxide is formed. Okay, so this one is a typo. It's supposed to be a hydrocarbon. Okay, so a hydrocarbon contains only carbon and hydrogen. When 2 grams of the hydrocarbon is burned, 6.6 grams of the carbon dioxide is formed. Determine the empirical formula. Now, the empirical formula is the simplest whole number ratio. Okay, it's the simplest that you can have for a formula. The molecular formula is the actual formula of a compound. Okay, so now let's solve this question. We've been given those figures. So the way we find the empirical formula is, number one, you're supposed to find, okay, this is the same question. Yes, I think I'm going to solve it from here because there's of space. Number 1, we're supposed to find the moles of carbon dioxide, what we have. Okay, so the moles of carbon dioxide, it will be equals to, you know how to find the moles is mass over the molar mass. In this case, the molar mass, the mass for carbon dioxide, we've been given that it is 6.6 grams of carbon dioxide. Okay, so I'm going to put 6.6 grams of carbon dioxide. Then the molar mass for carbon dioxide, so carbon is like 12, oxygen that is like 16, that is like 32. Okay, so this will give me 44. So carbon dioxide, the mass is about, the molar mass is 44 grams per mole. Now what is now going to happen is that the gram and the gram are going to cancel. I'm just going to have 6.6 divided by 44. This will give me 0.15 moles. Okay, now that we found that, we can also find the moles of carbon. Okay, so in this case, what would be the moles of carbon? So from the carbon dioxide that we found, 1 mole of carbon dioxide contains 1 mole of carbon. Okay, so the moles of carbon will also be equals to 0.15 moles. Okay, that is very important. Now that we found that, what that means, now we can also now find the mass of carbon. Okay, the mass of carbon, because we have now the number of moles. In this case, the mass, how do we find the mass? You are going to have what you have as the number of moles multiplied by the molar mass for carbon dioxide, for carbon actually alone. So for carbon is going to be 12 grams. So in this case, 0.15 moles multiplied by 12 grams. In this case, I'm going to have 1.8 grams of carbon. Then we're also supposed to find the mass of hydrogen. So the mass of hydrogen, I'm just going to write H. Now the mass of hydrogen, we have to go back to the mass of the hydrocarbon. Okay, the mass of the hydrocarbon we've been given, it is 2 grams. Okay, and then since it is 2 grams, what will be the mass of hydrogen? So the mass of hydrogen here now is just going to be 2 minus 1.8 grams. Okay, for us to find the mass of hydrogen. Now why we are subtracting this is because the whole hydrocarbon, in terms of the mass, we've been told that it is 2 grams. We've already found the mass of carbon. So now, for us to find the mass of hydrogen, we just have to subtract from the actual mass. That's why we're subtracting. In this case, I'm going to have 0.2 grams. Okay, so that will be the mass of hydrogen. Then the number of moles, in this case, the number of moles of hydrogen is just going to be, you know how we find the number of moles? It's going to be the mass over, the mass is 0.2, then over the molar mass. Hydrogen has a mass of 1, okay, grams per mole. So in this case, it's just going to be 0.2 moles of hydrogen. Then from there, you're supposed to find the simplest whole number ratio. Okay, the simplest whole number ratio. Okay, how are we going to find that? So we've got C and we've got H. You'll see the moles for for carbon, we found that it was 0.15 Okay, then the moles for hydrogen, we found that is 0.2. Then you have to compare which one is smaller. Okay, which one is smaller? So in this case, what are we going to have? So 0.1 and 0.2. So we're going to divide by this 0.15 on both sides. But if you divide by 0.15, it's not going to help us so much, okay? Because we're going to just have zeros everywhere. Now we're going to, what we're going to do, we're going to choose a number that is going to give us at least a whole number, okay? Because we said this is the simplest whole number ratio, okay? That is the empirical formula. So I'm going to get 0.05. Why I'm picking 0.05 is because if I get 3 multiplied by 0.05, it gives me 0.15, okay? So that is my goal. So I'm going to divide by 0.05 on both sides. Now this will give me 3. Now there's the other one, 0.2 divided by 0.05, it gives me a 4. Okay, so therefore the empirical formula for this one, it is going to be C3H4. So basically that. However, if it was a molecular formula, you would have multiplied by, if you had a subscript there, to just multiply like that. So basically this is about stoichiometry. Now let's just review the formulas that we've talked about before we end. You have to understand the mole concept. We've talked about it. Here the formula is, we're talking about mass, or the moles. The number of moles will be equals to mass over molar mass. Okay, then if you're finding mass, it will be mass will be equals to moles multiplied by molar mass. Okay, so that's about the mole concept. Then you also have to understand that the number of particles, particles we said the atoms, molecules, ions, is going to be what you have as the number of moles multiplied by Avogadro's constant. And the Avogadro's constant we said is about 6.02 times 10 to the power 23. Okay, then you also have to understand the molar mass. Now the molar mass is one of those essentials. When we talk about the molar mass, we said the molar mass, the way we are going to find it is the sum of the atomic masses. Usually you are getting it from the periodic table. The unit is grams or gram per mole. Okay, then you also have to understand the chemical equations. Here we've said you always use a balanced equation, okay, because coefficients, they are going to represent also the mole ratios. So the mole ratios, these ones, you are getting them from a balanced equation. Moles required or formed. How are you going to find that? You are going to say the moles that you are requiring, or the ones that are formed, will just be given by the moles that you've been given multiplied by the coefficient ratio. Okay, basically that. Then mass to mass, here how to convert mass to moles, how to use mole ratio, and how to convert moles back to mass. That is what you're supposed to do. Then we also talk about the limiting reagent. Here we are converting all reactants to moles. Then after you've done that, you compare using mole ratios. Then the reactant that produces the less product is what we are calling the limiting reagent. Then percentage yield, we are saying this is the actual yield over the theoretical yield times 100%. Then we talked about concentrations of solutions. Here we said the concentration, you're going to find it by the moles divided by the volume. Okay, the unit for concentration is mole per liter. Okay, that is very, very important for us to understand. Then what about mole in solution? When we're talking about mole in solution, moles is equals to, if you're going to find the moles in a solution, it's just the same formula. Moles is going to be the concentration that you have multiplied by the volume, and this volume must be in liters, and 1 liter is about 1,000 cubic centimeters. That is very important. Then we further on talked about stoichiometry, in this case the solution part of stoichiometry. Here we're talking about us finding the moles using the concentration, using mole ratios, also calculating the required volumes or concentrations. Then lastly we talked about combustion analysis, where we're talking about empirical formula, basically those very important details. Then let's solve some questions on what we've talked about. So we've got the mole concept and particles. How do we solve these type of questions? So these ones are comprehensive questions based on what we've done. Okay, so now the first question is a sample contains 2.20 grams of carbon dioxide. Calculate the number of moles of carbon dioxide in the sample. Determine the total number of oxygen atoms in the sample. Calculate the mass of carbon in the sample. If the sample is increased to 11 grams, how many molecules are present? Then we're told to explain why the Avogadro's number is essential in converting between moles and particles. Okay, so let's start with the first part. We are told to calculate, we've been given 2 grams of carbon dioxide. Okay, so we're told to calculate the moles of carbon. Now, how do we do this? Okay, so you know that the moles of carbon dioxide. So what is the molar mass, first of all? Because the number of moles is equals to mass over molar mass. In this case, the mass we've been given that it contains 2.2 grams of carbon dioxide. So in this case, we're just going to have we're saying the mass, the number of moles, because we're calculating the number of moles will be equals to mass over molar mass. The mass is 2.2 grams, okay, over the molar mass. The molar mass of carbon dioxide, we've been calculating it so much. So what is it going to be? We've said it's roughly about 44 grams, okay. So if it's roughly 44 grams, how we found it is carbon is 12. We're saying carbon dioxide, carbon is 12, oxygen is 16, but we've got two oxygen, so I'm going to multiply by 2. That is 12, that is 32. That will give us a 44 grams per mole. That is how we find the molar mass. So I'm going to put 44 grams per mole there. Now when we divide 2.2 grams divided by 44 grams per mole. So the gram and the gram are going to cancel. I'm just going to remain with moles. So therefore, what do now I have? I've got 0.05 moles. Okay. So the first part of the question gives me 0.05 moles. So those are the moles of carbon that we are going to get. Then question number 2, we are told to determine the total number of oxygen atoms in the sample. Okay, the total number of oxygen atoms in the sample. Now, if you are going to look at the sample itself, carbon dioxide as a molecule, okay, how many oxygens does it have, because it's a sample that we're talking about. It has 2 oxygens, or 2 oxygen atoms. Now, the number of molecules determine the total number of oxygen atoms. Okay, every time we're talking about atoms, molecules, ions, I'm sure it now rings a bell. Okay, the Avogadro's number is going to come in. Okay, so in this case, the number of the atoms of oxygen or molecules is just going to be the moles, or the number of moles multiplied by the Avogadro's number. So in this case, the moles that we have for oxygen, what do we have? Have we been given in the question? Of course not, we haven't been given. However, we're going to take it that it has the same moles of carbon dioxide. Okay, basically that, because it's in the same sample. Okay, it's in the same sample, this one. So the moles of carbon found that is 0.05. So we're going to multiply this by the Avogadro's number, which is 6.02 times 10 to the power 23 atoms. Okay, now what do we have? 0.05 multiplied by 6.02 times 10 to the power 23. So I'm getting 3.01 times 10 to the power 22 molecules. Okay, basically this, now we have to consider something here. We have 2 atoms of oxygen, we've only found for 1, so we're going to multiply this now by 2. Okay, what we have as the answer by 2, because there are 2 of them, so we're going to multiply by 2. So the answer that I have multiplied by 2, I'm getting 6.02 times 10 to the power 22 atoms. So basically it's going to take me back to the Avogadro's number. Okay, close to the Avogadro's number. So basically that's how we solve this one. We are saying it's going to be we're saying B. We're saying okay, that is 6.02 times 10 to the power 22 atoms. Okay, then C, we are taught to calculate the mass of carbon in the sample. The mass of carbon in the sample. So the sample is still the same. We're talking about carbon dioxide. So the moles of carbon, we've already found that it is the moles of carbon of the carbon dioxide itself is 0.05 moles. Okay, you know that for us to find the mass, we know that number of moles is equals to mass over molar mass. In this case, the mass will be equals to number of moles multiplied by the molar mass. In this case, the number of moles that we found, it is 0.05 moles multiplied by the molar mass for carbon, it is 12. Okay, so 0.05 moles multiplied by 12, that will give us 0.6, grams, because this is grams per mole. The mole and the mole are going to cancel. So therefore, for this one we have 0.6 grams. And then we come to D. If the sample is increased to 11 grams, how many molecules are present? Okay, so it's not really something that is complicated. You've just increased it to 11 grams. So in this case, the number of moles is equals to mass over molar mass. So we have to first find the number of moles, because it's the one that is going to help us find the number of molecules. So in this case, the mass has been increased to 11. Okay, then the molar mass for carbon dioxide, it is still 44 grams per mole. So in this case, when you divide, we're finding 11 divided by 44, that is 0.25 moles. Now that we found the number of moles, how do we find the number of molecules or particles? Okay, we've been talking about this one. You're going to get the number of moles, 0.25 moles multiplied by the Avogadro's number, 6.02 times 10 to the power 23. Then you calculate. So we have 0.25 already punched, multiplied by 6.02 times 10 to the power 23. I'm getting 1.505 times 10 to the power 23. Since these are molecules, it's molecules. So I'm going to write that answer here, 1.505 times 10 to the power 23 molecules. Okay, then we come to E. Explain why Avogadro's number is essential in converting between moles and particles. Now, the Avogadro's number, if you're going to look at it, it allows conversion between moles. Moles are, these are very, very, or say the mole is just a counting unit, it's big. And actual particles, the actual particles, we're talking about atoms, molecules. Making chemical calculations is very possible. That's why, it's very essential to know this, the Avogadro's number. So basically, that's how we solve those ones. The more concept and the particles. Let's solve another set of questions. Mass to mass calculations. So how do we solve these ones? We are told ammonia is prepared by the reaction of nitrogen with hydrogen gas. Then the reaction is there. Then we are told to write the balanced chemical equation to calculate the moles of ammonia formed from 28 grams of sodium of nitrogen. Then to determine the mass of hydrogen required to react completely. Okay, so let's just start with the first one, to write the balanced equation. Now, we've already been given a balanced chemical equation, because we're able to see here we've got two nitrogens there. Then when we come to hydrogens, we've got 6 here, also got 6 there. So it's already balanced. So the A is already balanced. We come to B, calculate the moles of ammonia formed from 28 grams of nitrogen. So if we're talking about nitrogen and the moles of first, since I've talked about nitrogen, we have to find the molar mass of nitrogen. We have to find the moles, actually, the number of moles of nitrogen. So in this case, the number of moles for nitrogen is just going to be the mass over the molar mass. The mass, they are saying, formed from 28 grams of nitrogen. So in this case, it's going to be 28 grams over the molar mass for nitrogen. What is it going to be? Okay. So in this case, nitrogen, the molar mass is going to be 28 grams per mole. Okay. So the gram and the gram are going to cancel. In this case, we're just going to have 1 mole of nitrogen. Now, if you look at the mole ratio, nitrogen has a coefficient of 1, and the product itself has a coefficient of 2. Okay, so then the ratio of 1 is to 2. So if the ratio is 1 is to 2, nitrogen gives us 1 mole. What about the product? Okay, what are we going to have? So in this case, we are going to realize that we're just going to have the moles of ammonia to be 2. Okay, so because for every mole of nitrogen, you're going to get 2 moles of the product. So in this case, the moles of ammonia that is going to be formed from 28 grams is just going to be 2 moles. Okay. Okay, so we're saying this is going to be 2 moles. Then C, determine the mass of hydrogen required to react completely with 28 grams of nitrogen, the mass. Okay, so what mass is going to be required to react completely with hydrogen, with nitrogen? So in this case, the mass of hydrogen that is going to be required is going to be, how many hydrogens do we have? Okay, so we've got 3 of them there. So in this case, in terms of moles, we're also going to use the coefficients. This has a coefficient of 1, this has a coefficient of 3. So for every mole of nitrogen, you're going to have 3 moles of hydrogen. So in this case, we're going to have 3 moles of hydrogen first. It's the one that is going to help us. This is hydrogen. It's the one that is going to help us find the mass. Okay. So in this case, what are we now going to have? The mass of hydrogen, therefore, is now going to be, you know that mass is equals to the number of moles multiplied by the molar mass. Okay. The number of moles, find that is 3. The molar mass for hydrogen, okay, is going to be what? So we're able to see that there are 2 of them. Here there are two hydrogens. The molar mass is 1, but because there are 2, I'm going to multiply by 2. Okay. Therefore, it's going to give me 6 grams. Okay, 6 grams is the one that is required. So here I can even put 6 grams. Okay, so that's how we find C. Then for D, if only 30 grams of ammonia is produced, calculate the percentage yield. Okay, so percentage yield. So for the percentage yield, let's first find the molar mass for ammonia. Okay, nitrogen, in this case it is 14, plus hydrogen, we have hydrogen is 1, the molar mass. Now it's because there are 3, I'm going to multiply by 3. Okay, so this is 14 plus 3. This will give me 17 grams per mole. That is the molar mass. Now, the theoretical mass, what is it? Okay, if we're going to look at ammonia, how many are there? There are 2, okay, that are produced. So in this case, since because there are 2, this we're going to multiply it by 2, 17 multiplied by 2. Okay, that will give us roughly like 34 grams. Okay, that is the theoretical mass. Now the way we're going to now find the percentage yield in this case is going to be, what have we been given, what did we obtain? We 30 grams was produced. Okay, so here 30 grams was produced, but the one that we've calculated is 34 grams. Okay, we're going to multiply this by 100, then you solve. Here I'm finding 88.2%. So basically this is how you find the percentage yield, 80%. Then E, we're told to explain one factor that can cause the reaction yield to be less than 100%. So there are a lot of factors. It can be, number 1, incomplete reactions. Okay, incomplete reaction. This is where maybe reactants that don't completely react. Also some side reactions. You can also loss due to maybe during handling or even purification. So those ones can also alter the percentage yield, what you're going to get at the end of the day. So let's solve the other part of questions. The limiting reagent and percentage yield. Now we're told magnesium react with sulfur to form magnesium sulfide. They've given us the formula there. It's already balanced. balance the chemical equation. So it's already balanced. Then define the limiting reagent. The reactant or the reagent that gets completely used up is the limiting reagent. It limits the amount of the product that is formed. That is what we are calling a limiting reagent. Then C, if 12 grams of magnesium react with 20 grams of sulfur, calculate the limiting reagent. Okay, so this is very interesting. 12 grams of magnesium reacts with 20 grams of sulfur. So please never assume because it has you don't assume because it has 12 grams then that it is the limiting reagent. You have to calculate basically that. So let's solve this one. So we are finding we already have we are first supposed to, what is the molar mass for magnesium? Okay, magnesium is about 24 grams per mole. Okay, then the molar mass for sulfur is about 32 grams per mole. Then let's now find the moles. The moles for magnesium. Magnesium in this case is going to be mass over molar mass. Even this other one, sulfur, is going to be mass over the molar mass. What have we been given for magnesium as the molar mass or as the mass? We've been given that 12 grams. Okay, so 12 grams divided by the molar mass, which is 24 grams per mole. Okay, so the grams and the grams are going to cancel. 12 divided by 24, that will give us 0.5 moles. Okay, then for sulfur, what are we going to have? Sulfur, the mass that we've been given is 20 grams, so it is 20 grams over the molar mass for sulfur we said is 32 grams per mole. Then we're just supposed to divide 20 divided by 32. What does this one give us? 20 divided by 32 is giving me 0.625 moles. Okay, now from the equation we're able to see that the ratio between magnesium and sulfur is just 1 to 1. Okay, so here we have to be very, very careful. So what this means is that what is needed for sulfur for 0.5 moles, we also need 0.5 moles of magnesium. Now look at the available for the sulfur. It's 0.625. So what this means is that from the equation, one more of magnesium always reacts with 1 more of sulfur to produce the magnesium sulfide. But now when we calculate the number of moles, the magnesium is given as 0.5, sulfur is given as 0.625. So able to see that this one is going to finish first before the other one even finishes. So in this case, magnesium is the limiting reagent. Okay, let's solve D. We are taught to calculate the theoretical mass of magnesium sulfide. Another interesting question, the theoretical mass. Okay, so what is the molar mass of magnesium sulfide? So magnesium we said is 24, sulfur is 32. So in this case the molar mass is going to be 56 grams per mole. Okay, then the number of moles now for this magnesium sulfide is going to be mass over the mass, the number of moles is going to be mass over molar mass. But we've already said the ratio is just 1 to 1, so it's going to get the same mass for the magnesium, which is 0.5 moles. Okay, now I'm supposed to convert this moles to mass. Okay, so you know that mass in this case is just going to be the number of moles that we have multiplied by the molar mass. So in this case, the number of moles is 0.5 multiplied by the molar mass. We found that it is 56 grams per mole. Okay, and this is mole. So the mole and the mole are going to cancel. 0.5 multiplied by 56, that will give us 28 grams. Okay, so basically those are the grams for, that's the theoretical mass for magnesium sulfide. Then E, we're taught to, if only 28 grams of magnesium sulfide is obtained, calculate the percentage yield. If only 28 grams of magnesium sulfide is obtained, calculate the percentage yield. Okay, so basically the percentage yield, we say percentage yield is equals to the actual over theoretical multiplied by 100. So in this case, the actual, we've been told that if only 28 grams is obtained, so that is the actual, the one that you obtain, 28 grams over the theoretical. After calculating, we found that it is also 28 grams multiplied by 100. Okay, so 1 it just give us 28 22 28, that is a 1, and we are just remaining with 100. Okay, so we have 100%. Although this is an ideal, so it's an ideal case. Okay, so basically that is what we have. So let's solve another set of questions. So in this segment, we are going to solve questions on solution stoichiometry. It's one of the most interesting topics. So we've got 25 cubic centimeters of 0.2 moles per decimeter cubed. Sodium hydroxide is titrated with sulfuric acid. Then we're taught to write the balanced chemical equation for the reaction, then to calculate the moles of sodium hydroxide in 25 cubic centimeters of solution, then to determine the moles of sulfuric acid required, to also find the volume of sulfuric acid required for complete neutralization, then also to explain why volume must be converted to dm cubed in calculations. So let's start with the balanced chemical equation. So okay, so let me just write it here. So we have sodium hydroxide. Sodium hydroxide is reacting with sulfuric acid. Then it gives us sodium sulfate plus, so this is sodium, this we're going to have 2 there, then we're going to have water. Now we have to balance this. In terms of balancing it, we've got 2 sodium atoms there, so I'm going to add a 2 here. Then we've got, what about hydrogens? This side we've got 2, even this side 2 hydrogens. We have 4 this side, so I'm also going to add the 2 there so that they become 4. We've got 2 oxygens plus 4, we've got 6. I come to the other side, I've got 2 oxygens plus 4, this is 6 as well. So basically everything is now balanced. That is the balanced chemical equation. Then B, were taught to calculate the moles of sodium hydroxide in 25 cubic centimeters of solution. Okay, so this is not very complicated. It's just that we need to convert some units here. The volume in dm, cubed is 20. It's 25 centimeter cubed. So now what are we going to do? It's the same thing, dm cubed or centimeter cubed. So in this case, I'm going to get my 20, my cubic centimeters, 25 cubic centimeters. I'm going to divide it by 1000 to convert it to dm cubed. Okay, so in this case, what am I going to have? 25 divided by 1000. I'm going to have 0.0. I'm going to have 0.025 dme cubed, or liters if you want. Now, what will be now the moles? The moles of sodium hydroxide will therefore now be, that we do the concentration multiplied by the volume. Okay, so in this case, the concentration we've been given in the question that it is 0.2 moles per decimeter cubed. That's why we're giving our answer in decimeter cubed, because they've also given us decimeter cubed there. So in this case, what are we going to have? We're going to have 0.2 moles per dm cubed multiplied by the volume. We just found the volume, which is 0.025 dm cubed. So the dm cubed and dm cubed I'm going to divide. Therefore, now what are we going to have as the number of moles? So in this case, 0.2 multiplied by 0.025, I'm getting 0.005 moles. Okay, so that is what I have. Then C, we are taught to determine the moles of sulfuric acid that is required. The moles, every time we're talking about the moles, please go to the mole ratios, you check. So if you're going to look at sodium hydroxide, it has 2 there. Okay, however, if you're going to look at sulfuric acid, it is 1. So for every 1 mole of sulfuric acid, you need 2 moles of sodium hydroxide. So in this case, what are we going to have? The moles of sulfuric acid will be also equals to what? The moles of sulfuric acid, in this case, is going to be what you have as the moles of sodium hydroxide, which is the one of just from finding, 0.005 moles. Now, because the ratio is 2, I'm going to multiply this by 2. Okay, 2, because this, for every mole of sodium, for every 2 moles of sodium hydroxide, you need 1 mole of sulfuric acid. So in this case, I already have my 0.005. I'm just multiplying it by 2. What do I have? I'm getting 0.0025 moles. Okay, basically those will be the moles. Then D, we are told to find the volume of 0.150 moles per cubic decimeters. So then there is of sulfuric acid required for complete neutralization. Okay, now what are we talking about here? The volume. So it's just about manipulating the equation. Okay, so in this case, the volume, that is equals to moles divided by the concentration, because concentration is equals to the number of moles divided by the volume. So yeah, so volume will be equals to number of moles divided by concentration. What is the number of moles that we have? Mind you, we're talking about sulfuric acid. We've already found the moles of sulfuric acid from the previous question. So if this is wrong, everything will be wrong. So here we have 0.0025. That's why we need to be very careful when you're solving these questions with babies. Then the concentration, we're told the volume of, find the volume of 0.15 moles per decimeter cubed. That's 0.15 moles per decimeter cubed. That is our concentration. So in that case, we're just dividing by 0.15 moles per decimeter cubed. So the more and more are going to cancel. So I'm just dividing. I already have my 0.025. I'm just dividing it by 0.15. So this is giving me 0.0167. Now since this is the volume, so it will be dm cubed like that. Okay, so basically that. Then for question E, we're told to explain why volume must be converted to dm cubed in calculation. So if you're going to look at concentration itself, concentration is defined as moles per decimeter cubed. That's the one that we've been given here. So it depends on what they've given you. If it's moles per liter, you have to understand. That's why we're converting that. So the volumes must be converted for consistency. That's what we're just talking about here. Okay. So now, just to sum up the video, let's solve the last part of questions. Okay, this is the empirical and molecular formula. Okay, so this will give us a good summary on this topic. We are saying a compound contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Its molar mass is 180 grams per mole. Then we're told to calculate the moles of each element in 100 grams of the compound. Then we are told to determine the simplest whole number ratio, which we also call the empirical formula. Then we're told to calculate the empirical formula mass, then to determine the molecular formula of the compound, then to explain why molecular formula may be a multiple of the empirical formula. Okay, so this is an interesting question. So let's start with the first question. We've been told to calculate the moles of each element in 100 grams of the compound. Okay, so let's start. What do we have? We've got carbon 40%, hydrogen, and oxygen, CHO. Okay, so we've got C, H, and O. Carbon, we're saying, is 40%, hydrogen 6.7%, oxygen 53.3%. So we are saying carbon is 40%. Hydrogen, we're saying it is 6.7%. Then for our oxygen, we're saying it is 53.3%. So what is now going to happen is that we have to convert these ones to moles. Okay, so the way we're going to convert these ones to moles, I'm going to take my percentages as if they are masses. Okay, so this will be 40 grams, this will be 6.7 grams, this will be 53.3 grams. So now what I'm now going to do is that after I've converted those ones to grams, it's very easy now to convert to the number of moles. Okay, so now let's convert them to moles. So to convert to moles, we know that number of moles is equals to mass over molar mass. The mass is 40 divided by the molar mass for carbon. Carbon is 12, right? Grams per mole. So the grams and grams are going to cancel. So the number of moles, here we're finding the number of moles. Let me just write it by the side. So this is moles. So 40 divided by 12, what does it give me? 3.33 moles. Then I come for hydrogen. I've got 6.7. Hydrogen has a mass of 1. So therefore, the moles of hydrogen is just going to be 6.7 moles. Then I come to oxygen. Oxygen has a molar mass of 16 grams per mole. So in this case, 53.3 divided by 16, I'm getting 3.33 moles. Okay. So basically this is what I have for now. Now what I'm now supposed to do is that I'm supposed now to introduce, I think the question is just asking us to find the moles. Calculate the moles of each element in 100 grams of the compound. Okay, so these are the moles. We found 3.33, 6.7 and 3.33 again. So carbon, we found that it is, let me use a different color. Carbon, we found that it is 3.33 moles. Then hydrogen follows. We found that it's about 6.7 moles. Then oxygen follows. We found that it is also, it's the same as the carbon. Okay, so that is what we have. Then B, were taught to determine the simplest whole number ratio. Okay, so whatever we have, we now have to find the ratios. Okay, so we're just for us to find the whole number ratios, we're going to divide everything by the smallest. So I'm just going to call this one ratio. Okay, if we divide this one by the smallest here, we're able to see that it's 3.3. So it's 3.33. Also this one divided by 3.33. Also this other one 3.33. So what are we going to have as our ratios? This is going to give us 1. 6.7 divided by 3.33. I'm getting 2. Then this one is also going to give us 1. So we're taught to determine the simplest whole number ratio. So the same whole number ratio is what is going to give us the empirical formula. So in this case, what is the formula then? It's going to be C1 H2 O1. Then when you simplify it, it's just going to be CH2O. So this is what we are calling the simplified whole number ratio. It is CH2O. Okay, so that is how we find that. Then we're told to calculate the empirical formula mass. Okay, so how then do we find the empirical formula mass? So we just have to add the masses for what we have as our compounds. Let me just remove this. So we have CH2O. Okay, that is what we have as a compound. Okay, that's the empirical formula. This question is asking us to find the mass of this empirical formula. So in this case, we have carbon. Carbon has a mass of 12 plus hydrogen. Hydrogen has a mass of 1, but because there are 2, I'm going to multiply that by 2. Plus oxygen has a mass of 16. So I'm going to have 12 plus 1 multiplied by 2. That is a 2 plus 16. Now 12 plus 12 plus 2, that is 14 plus 16. Then if we were to add 14 plus 16, that is 10, that is 30. So the mass of this compound is a 30. Okay, So basically 30 grams. Okay, we're saying this should be 30 grams. The empirical formula mass, 30 grams. Okay, and then D, we're told to determine the molecular formula of the compound. The molecular formula of the compound. Now, how do we find the molecular formula of the compound? Okay, so molecular formula is going to be the first before we talk about the molecular formula, the number of moles in this case. We've got N. N is goes to molar mass over empirical mass. The M is there's a number that is usually at the end when you're calculating the molecular formula. N will be equals to, now what is the molar mass and what is the empirical formula mass? So basically for your molar mass, you always try to go back to the question to find out. Okay, so they've given us that its molar mass is 180 grams per mole. Okay, so that is the molar mass we're talking about here. So what is the molar mass? So excuse me for that. Okay, so excuse me for that. So we are asked okay, so yeah, the molar mass. So the molar mass, it is 180 grams per mole, right? Grams per mole. Then the empirical formula mass is the one that you're just from calculating. Did you even write it? Yes, we found that it was 30 grams. What did I even write? 30 gs. So this is 30 grams. So the gram and grams are going to cancel in this case. So in this case, what do we now have? We've got 180 divided by 30. So I'm just going to cancel the zeros. Then 3 into 3 is 1. 3 into 18, that is a 6. Now we have a 6 as our coefficient n. So in this case, what are we now going to have? We're going to write now our molecular formula. First, get your empirical formula. In this case, our empirical formula is CH2O. Okay. Now we have 6 there. We're going to multiply this by 6. Okay. Of course, what we have as the subscript. So in this case, I'm going to have, when the 6 multiplies with the C there, okay, I'm going to have C, then the 6 down there. Here we've got H, and there's a 2 there, so I'm going to write my H. Now the 2 multiplied by the 6, that will give me a 12. Then we've got O. We're going to have a 6 there. So that is how we find the empirical and the molecular formula. Basically this one for the molecular formula. And you know that this formula is for glucose, right? Yes, so that formula is for glucose. Okay. Now we've got the last question, which is E. Explain why molecular formula may be a multiple of the empirical formula. Why is it that molecular formula may be that of the empirical formula. So we have to understand that molecular formula is a multiple of the empirical formula, because molecular formula itself, it shows us the actual number of the atoms, which may be a whole number multiple of the simplest ratio. Okay, so like this one is the actual. Okay, that's why the formula itself, you know, the molecular formula, it may be the whole number multiple of the simplest ratio. We have to see that we have to multiply. So basically that is the reason there. So I think we're done for this video. Please don't forget to subscribe and also like and comment. See you in other sessions.